Nuclear power, the dominating source from which we are able to power our homes. But what about its devastating effects? What about its influence on nuclear war? Can nuclear power exist without nuclear weapons? An up-and-coming scientist, Taylor Wilson, has made significant strides in the nuclear power industry and may be able to answer some of our questions. A discussion on Taylor Wilson's innovative ideas. Taylor Wilson was born May 7, 1994, and is an American nuclear scientist and science advocate. From a young age, he was very interested in the world of science and became passionate about making a difference in the world. At the age of 14, he became the youngest scientist to create a nuclear reactor, and since then has worked on many nuclear projects. In 2010, he won several awards for his project, Fission Vision, at the Intel International Science and Engineering Fair in California. He would later win $50,000 in reward money for his project Countering Nuclear Terrorism, novel active and passive techniques for detecting nuclear threats. He is active in the field of counterterrorism and hopes to create safe, affordable energy which can be used to create a nuclear weapons-free world. He has worked on many types of reactors, including fusion reactors as well as fission reactors. Some of his projects that we will be discussing are the Inertial Electrostatic Confinement Reactor and the Dense Plasma Focus. Although these reactors are very interesting, we will be mainly focusing on his molten salt reactor, a project that he considers to be very promising for a nuclear weapons-free world. The inertial electrostatic confinement. This was one of the first successful fusion devices that Wilson built. The structure of this reactor consists of an ultra-high vacuum system, which removes the majority of air molecules from the fusion chamber. Air is pumped out with a series of vacuum pumps, and small amounts of fusion fuel enter the reactor and become ionized. Once they have entered and become ionized, a high voltage supply creates the electrostatic potential that heats and attracts the deuterium ions to the center of a grid made of a special high melting point of 98% tantalum and 2% tungsten. The fuel that is used is a stable, naturally occurring isotope and has been isolated and enriched with natural water. This fuel is unique because, unlike many other nuclides found in nature, deuterium atoms aren't made in an active cosmic process. They exist in their current state. The dense plasma focus has power that is dumped into a set of coaxial electrodes in a higher pressure gas environment than an IEC. It generates a hot, turbulent plasma filled with complex MHD instabilities, compact balls, and toroids of plasma and energy. Wilson states that the plasma focus is a poorly understood phenomenon. His primary interest in these reactors came from the chaotic instabilities that they create.
About how nuclear fission works. In a nuclear power plant, you have a big pot of water that's under high pressure, and you have some fuel rods. And these fuel rods are encased in zirconium, and they're little pellets of uranium dioxide fuel. And a fission reaction is controlled and maintained at a proper level, and that reaction heats up water. The water turns to steam, steam turns a turbine, and you produce electricity from it. This is the same way we've been producing electricity, the steam turbine idea, for 100 years. And nuclear was a really big advancement in a way to heat the water, but you still boil water, and that turns to steam and turns a turbine. And I thought, is this the best way to do it? Is fission kind of played out, or is there something left to innovate here? And I realized that I had hit upon something that I think has this huge potential to change the world. And this is what it is. This is a small modular reactor. So it's not as big as the reactor you see in the diagram here. This is between 50 and 100 megawatts. But that's a ton of power. That's between, say, at an average use, that's maybe 25,000 to 100,000 homes could run off that. Now, the really interesting thing about these reactors is they're built in a factory. So they're modular reactors that are built essentially on an assembly line, and they're trucked anywhere in the world. You plop them down and they produce electricity. And this region right here is the reactor. And this is buried below ground, which is really important. For someone who's done a lot of counterterrorism work, I can't kind of extol to you how great having something buried below the ground is for kind of proliferation and security concerns. And inside this reactor is a molten salt. So anybody who's a fan of thorium, they're going to be really excited about this because these reactors happen to be really good at breeding and burning the thorium fuel cycle, uranium-233. But I'm not really concerned about the fuel. You can run these off. They're really hungry. They really like downblended weapons pits. So that's highly enriched uranium and weapons-grade plutonium that's been downblended. It's made into a grade where it's not usable for a nuclear weapon, but they love this stuff. And we have a lot of it sitting around because this is a big problem. You know, in the Cold War, we built up this huge arsenal of nuclear weapons, and that was great. And we don't need them anymore. And what are we doing with all the waste, essentially? What are we doing with all the pits of those nuclear weapons? Well, we're securing them, and it would be great if we could burn them, eat them up, and this reactor loves this stuff. So it's a molten salt reactor. It has a core, and it has a heat exchanger from the hot salt, the radioactive salt, to a cold salt, which isn't radioactive. It's still thermally hot, but it's not radioactive. And then that's a heat exchanger to what makes this design really, really interesting. And that's a heat exchanger to a gas. So going back to what I was saying before about all power being produced, well, other than photovoltaic, being produced by these boiling of steam and turning a turbine, that's actually not that efficient. And in fact,
it all sounds pretty good, right? But what about the environmental risks? What about the health hazards? Although Wilson does not go into detail about the environmental effects or the health hazards, he still has some good points that should be considered. For example, efficiency. Because it operates at such high temperatures, it is able to be 50% more efficient than a traditional nuclear reactor. Because of this, it is able to have a more compact core because it transfers heat more easily at this high temperature. It is portable and compact. Because of its smaller core and reduced size, it is easily manufactured and shipped to anywhere it needs to go. A traditional nuclear reactor needs to be near a large body of water, as well as be encased in a very large and heavy container and cannot be moved easily. His ideas are innovative. The ideas that can be linked and shaped from this reactor show strong promise because it is the first step in taking thinking away from the traditional nuclear reactor. Mainly, however, can this type of nuclear reactor really be implemented and influence a weapons-free world? Well, we think so. It is a sealed system, which means that for 30 years it can stay under the ground and only be removed when it needs to be refueled. Due to the lack of pressure, as this reactor operates at atmospheric pressure, it is able to be stored under the ground, where it is less visible and not easily found. The waste that it produces is stored underneath the reactor, making it even less accessible to anyone who may want to find it. Lastly, and the most important point of all, is that the fuel it uses is a downblended form of weapons-grade uranium. Therefore, if found and accessed, the fuel it uses will not be useful. After researching Taylor Wilson, a passionate and innovative young scientist, we think that this molten salt reactor could be the start of creating energy sources that influence a weapons-free world.